Here we are on page 7 and 8. And here we're going to continue to do differentiation problems, but they're giving it to us in word problems. Point P lies on the curve y equals x squared plus 3x minus 4. The gradient of the curve at P is equal to 7. Find the gradient function of the curve. Find the x and y coordinates of P. So basically what they're saying is they have a curve. And on that curve, they're saying there is a point where if they drew the gradient line of that point, or the tangent line of the point, the slope of that gradient line would be 7. So they're saying, when is the slope of this parabola equal to 7? The way you can find that out is, we know how to find the gradient function of the parabola. We find it by doing differentiation. So the first thing we do is what we've been doing, practicing the last few pages, which is we take the derivative of x squared plus 3x minus 4, which turns out to be 2x plus 3. So we have a function which gives us the gradient of the parabola at any point. And then we just want to know, when is that gradient 7? So one of the easiest ways to do this is with the calculator. So we put in the calculator the gradient function. And I put the original function in here, but we're not going to graph it yet, so I turned off the graphing for the original function. I only turned on the graphing for the gradient function, which is 2x plus 3. Now I'm going to graph it, and this is the gradient function. When is this gradient function equal to 7? Well, there's a couple ways to do this, especially with a nice, easy function like this. One is you could do trace, and then you could just move the cursor until you get to y equals 7. But it's hard to get 7 exactly. We can see that it's about equal to x equals 2, but we're not sure. So we could use second table to be more sure, because in table it'll show you the whole number increments of x with the corresponding y. And what do you know? When the gradient is 7, x is 2. So the answer to B is 2. X equals 2. What does y equal when x is 2? Well, you might look at this and you say, oh, y equals 7. But no, this is the gradient function. It's not the original function. Now we need to look at the original function. What is the y value in the original function? Well, we programmed the original function here into y1. Now we'll turn on graphing for that. Hit enter on top of the equal sign. And then we'll graph it, and we'll see both the original function, which is a parabola, and the gradient function of the parabola graphed on the same plane. Now, what does the parabola y value equal to when x equals 2? We know that the gradient function is equal to 7, right? But we did not figure out what the parabola equals to when x equals 2. And the way we can do that is, again, with table. So now if we look at table, we can say, okay, this is the parabola here, and this is the gradient function of the line. When x equals 2, the gradient is 7. That's exactly the point we want. When x equals 2, the y value of the original function is 6. Okay? So, we know that the y value here is going to be 6. So the value of point P is 2, 6. Okay? Now, there's a way you can do that with algebra. If you like doing algebra, then what you do is, okay, you say y equals 2x plus 3. And if you've done it with a calculator, you don't have to do this, but okay, y equals 2x plus 3. When does 2x plus 3 equal 7? So you write 7 in there because we're looking for the gradient. When does the gradient equal 7? What x gives us 7? And then we just do our algebra. We subtract 3 from both sides. We get 4 equals 2x. So x is equal to 2, right? How do we get the y coordinate for x equals 2? Well, we don't put x back into the gradient function. We have to put it back in the original function. The original function, which is y equals x squared plus 3x minus 4. And then we're going to put 2 back in here, so we get y equals 2 squared plus 3 times 2 minus 4. And that'll give us 6. Okay, just like from the calculator. Okay, moving on. Next one. We have this function, and then the first thing, and it asks you, when is the gradient of the curve equal to negative 3? So we need to find the gradient function and set it equal to negative 3. And on the test, it helps if you, here's the gradient function, by the way, 3 minus 2x. you can get a guaranteed point if you put -3 equals 3 minus 2x, because this says, I understand that I'm looking for when is the gradient function equal to -3. Okay, so even if you screw up the algebra or the calculator operation afterwards, this will get you a point. Okay, so you can do this with algebra, as you can see, or we're going to put it in the calculator. So in the calculator, I think it always helps to put both functions in the calculator. And then you have to kind of keep them straight, okay? Remember, let's see. I like to put the original function in 1 and the gradient function in 2 because it's easier to keep track of. So the original function is 4 plus 3x minus x squared. And then the gradient function is 3 minus 2x. 3 minus 2x. Graph it. I should see a parabola as the original function and a line as the gradient function. Okay, then it says, find the gradient function of the curve. We already did that. We wrote it down. The coordinates of r are a, b. Find the values of a and b. And what is it about r that makes it r? The gradient of the curve at point r is -3. So when is the gradient function, the line, equal to -3? Well, let's see if the table can tell us again. Okay, so when is the gradient function equal to -3? And remember, the second one I usually put the gradient function. So -3, so it corresponds to x equals 3. So at the point x equals 3, the gradient function is equal to -3. Well, what is the y value? What is the y value from the original function at x equals -3? It's 4. Okay, so what we see here is, and let's look at the graph again. So we have a graph. It looks about like this. Okay, so it just so happens at 3, 4, which I don't know if it's like this point here. There, the gradient is going to be -3. Okay, so the gradient line at this point is -3. And we can find that by looking at the gradient function, which is the line, and seeing, oh, it's -3 right here. -3 right here. Okay, so do you see how that works? The y value of the original function is 4, but the gradient function y value is -3 because the gradient function y value is the gradient of the parabola. Okay, that might be confusing. So just think, okay, when I make the table, the first column is going to be the y value for the original function. The second column is going to be the y value of the gradient. So when they say gradient, look in the second column. When they say what's the y value of the original function, look back in the first column. Okay? All right, number 5. Number 5. Now we're going to do this function, which is 3x squared plus x minus 5. Find the coordinates of the point on this function when the gradient is 4. And they don't ask you to find the gradient function here, but you always need to find the gradient function to do these problems. So the first thing we're going to do is find the gradient function, which is going to be 3 times 2x plus 1, which is the same thing as 6x plus 1. So that's the gradient function. I'm going to put y prime for that. And the original function is this. And I'm going to program both of those in the calculator. Okay, so I programmed the original function, the quadratic, 3x squared plus x minus 5, into y1. Then I programmed the gradient function, which we found through differentiation, in for y2. Then I graph it. And of course I see a parabola and a line. The line is the gradient function, of course. Now I want to see, when does the gradient function equal to 4? So I can see that easily with the table. So I'll do second table. And then I look at, when is the gradient function equal to 4? This is a tricky one. Do you see? Because I look here, and 4 is not one of the numbers that comes out for y2. Okay? So the way I would do it here is, now I need to find, when does the second function equal to 4? And this I can do with, now I am going to draw another function on the graph, which is, when is y equal to 4? Okay? And then just to make the graph less cluttered, I'm going to turn off the original function from the graph. Okay, I do that by hitting enter on the equal sign here. Then I graph it. Now I'm just going to see the line, and I'm going to see a line representing y equals 4. So now I'm saying, when does this line equal to y equals 4? And the way I do that is I do it with the intersect command. So I do second calc intersect, which is 5. And then I say, oh, the intersection between the second curve, enter. I just hit enter 3 times. And it tells me that the intersection of this line and this horizontal line, which represents y equals 7, is x equals 0.5. Okay, so x equals 0.5 is the x coordinate. Okay, and now how could I have done that with table? Well, I could have done it with table by saying, okay, I'm sorry, just ignore this because this is the y equals 4 function. Okay, so if I look at, just so it doesn't distract you, I'm going to turn it off. I'm going to turn off y equals 4 so that it doesn't appear in the table. Okay, so I'm looking at the gradient function, and I'm saying, when does the gradient function equals 4? I can't see it here because there's not enough finer increments of x. So what I'm going to do is I'm going to change the increment of x. So I'm going to say plus 0.5, and I'm going to make x jump by 0.5. And there it is. You see? Now I can see that the x value, which yields a gradient of 4, is going to be 0.5. Okay? Now, I did it the other way doing the graph. I drew the line to see when it intersects y equals 4. So either of those two ways is fine. Now I'm going to turn back on the original function in the graph and the table, because now I need to know what is the y coordinate of the function when x equals 0.5. And so I turn back on the function, and then I do second table. And then I can see that in the original function, at x equals 0.5, y equals negative 3.75. Okay? Now, let's look on the graph for that. Okay, so now we're going to have the parabola, the original function, and we're going to have the gradient function, which is the line. So, when is the gradient function equal to 4? It's equal to 4 at x equals 0.5. What is the value of the parabola at x equals 0.5? It is negative 3.75, which we found using the table. It's hard to see on the graph. Okay, so if you want to write the coordinate of the point as an ordered pair, you would write 0.5 comma negative 3.75. Okay, moving on to number 7. There are 2 points on the curve, y equals x cubed plus 3x plus 4, at which the gradient of the curve is 6. Okay, so this is the same kind of problem. It's just that with this particular function, there's more than 2 points that have the same gradient. Okay, when you have a parabola, then the gradient at any point is different. Okay, but when you have a cubic function, that's not true. If you say when is the gradient equal to 6, you're going to get 2 points, not 1. Okay, so again, you're going to do the same thing. We are going to program into the calculator the original function and the gradient function. And then we're going to see when is the gradient function equal to 6. Okay, so I'm just going to find the derivative first. When I find the derivative of the original function, I get 3x squared plus 3. Okay, then I'm going to program both the original function and the gradient function into this table. Okay, so now I have the original function, 3x cubed plus 3x plus 4, and for y1, and then I have the gradient function, 3x squared plus 3, in for y2. And first, I'm just going to graph the gradient function, because the gradient function is the one that I need to see when is it equal to 6. I graph it, and it's a parabola, because the derivative of a cubic function is a parabola like you found in the investigation. When is this parabola equal to 6? Let's look on the table to see if we can easily see that. And remember, we had changed the increments, the step size to 0.5. We can change that back if we want to. We can just change it to 0.5 when we need to. We do that by pressing plus. So you can see, when does it equal 6? Well, it's equal to 6 at x equals 1. But it asks, when is it equal to 6? What 2 points make it equal to 6? And you're saying, well, there's only 1 point here. Well, if you go up, there it is. Remember, a parabola is symmetrical. So if it equals 6 at a certain point, there's a reflecting point, which happens to be -1, where it's also equal to 6. So the 2 points are x equals -1 and x equals 1. At x equals -1 and at x equals 1, the gradient of the curve is 6. Now we need to find the original coordinate for these points. Okay, so the y-coordinate for these points on the original function is not going to be y equals 6. It's going to be, we're going to turn on this function, which is the original function. Now we want to know the y value of the original function. So we graph it, and the original function is a cubic function, which looks like a curve, kind of like an S curve. Now we're going to say second table again, and this time we're going to say, okay, what is the original function value for the points x equals -1 and x equals 1? And for x equals -1, it turns out to be -2. Okay, so -1 comma -2. What about for 1? For 1, it's equal to 1 comma 10. Okay, so those are the 2 points on the graph which have gradient function of 6. So for example, if you draw the original function, it looks kind of like this, right? Now, at what points is the gradient equal to 6? Well, if you drew the slope 6, it looks kind of like that. So you can see that it would be about here, and it would be about here. So like these are the 2 points where the original function has a gradient of 6, and those 2 points are these 2 points. Okay. Now number 9. There are 2 points on the graph, on the curve, x cubed minus 12x plus 5, at which the gradient of the curve is 0. Find the coordinates of these 2 points. Find the equation of the straight line that passes through these 2 points. So this has one extra step on it. So the first step, of course, is to find the derivative of the original function. So there's the original function, and the derivative is going to be 3x squared minus 12. Okay, and then that's it, right? That's the derivative. We're going to program both this function and this function into the calculator. Then we're going to find the x-coordinate, which makes the derivative equal to 0. Remember, on the test, what might help is you say, hey, I'm going to put equals 0 here because I'm trying to find when the gradient of the curve is 0. Okay, and then they'll know that you know what you're doing. So I'm just going to program both of these equations into the calculator. Okay, so here's the graph of the original function and the gradient function. And it's a little bit zoomed in, so I'm going to do zoom fit. If I do zoom fit, then I'll be able to see. Okay, so there is the original function. It's a cubic. And then the gradient function is a parabola. Okay, so the first thing is, when does the gradient function equal to 0? And so we can see that on the table. The gradient function is this one here, the second function. So when is the gradient function equal to 0? It's equal to 0 here, it's equal to 0 here. So it's at x equals 2 and x equals -2. So it's at x equals -2 and x equals 2. Those are the 2 places that the gradient function is equal to 0. Then it says, find the coordinates of these 2 points. So then we want to find the y value on the original function. The y value of the original function was x equals -2 is at y equals 21. And then for x equals 2, the y value is -11. Okay, so the 2 points are -2 comma 21 and 2 comma -11. Then the last thing it says, find the equation of a straight line that passes through these 2 points. Now remember, there's an easy way to do that. You use the stat function. You program both points into the stat edit screen. You're going to put -2, and then you put 11, -2 comma 21 actually. And then you put the other point is 2, -11. -11. So we program both points in the stat edit. Then we use linear regression to connect a line between the 2 points. We use stat, calc, linreg, which is 4, and the data is in the x coordinates are in L1, the y coordinates are in L2. Go down to calculate, and it gives us the function. It'll say y equals negative 8x plus 5. Okay? Next one. Okay, we'll read through this. The original function is this, x squared minus 3x minus 3. It says find the value of b. The value of b is, let's see, it's the y value when x equals 5. Then it says find the gradient function, and then it says find, okay. All right, this is let's take it one step at a time. So it says find the value of this function when the x value is x. And that's pretty easy to do with the calculator. So we're going to program this function into the calculator. And by the way, they ask us to find the gradient function, so we'll just do that now because we can do that. It's y prime equals 2x minus 3. Okay? And then we're just going to program that both of those into the calculator, the original function and the gradient function. This is getting repetitive, isn't it? Every time we're going to program both functions into the calculator. So we'll do a table. Okay. And, okay, so first thing they say, what is b when x equals 5 on the original function? So let's see, when x equals 5, I just need to scroll down a little bit to where x equals 5. What is the original function equal to? It's equal to 7. Okay, so the original function, or the value of b here is going to be 7. Okay, then it says, find the gradient function, and we just found it. Then it says, show that at p, the gradient of the curve is also equal to b, is also equal to 7. And we can see that here on the calculator, that by coincidence, at the point 5, 7 of the original function, the gradient is also 7. But they want us to show that. So to show it, we would need to do that by hand. And so we'll say, oh, well, at the x coordinate of 5, we just substitute 5 into here. Okay, at x equals 5, we're going to substitute 5 in there. And we'll get 2 times x minus 3, which is 2 times 5 minus 3, which is equal to 7. What do you know? So we've just proven that the gradient at x equals 5 is also equal to 7. The original function is also equal to 7. Then it gives us one more point, q. Q is the point of the curve at which the gradient of the curve is equal to negative 3. Show that d is also equal to negative 3. Okay, so that we can see also, they just tell us, hey, at x equals negative 3, or x, at some point, not at x equals negative 3. Oh, here it is. You see? When the gradient is negative 3, the function is also negative 3. What a coincidence. Okay? So what is the x value that causes that? It's equal to 0. Okay? So at the point 0, comma negative 3, the gradient is negative 3, right? Okay. And so we found it with the calculator. Okay, so how can we show that this is all true? Well, now that we know the point, now that we know that q is 0, negative 3, now we just need to plug these points into the formulas to show that they're equal. So first we do that with the original equation. We're going to put 0 and negative 3 in the original equation to show that it's true. So negative 3 equals 0 squared minus 3 times 0 minus 3, and that works out, right? So we've proven that this is a point on the original function. Then we take, then we say that, hey, at this point, y prime is equal to negative 3 also, and then we use the gradient function to show that. So we say negative 3 equals 2 times 0 minus 3, and that is also true, right? So now we've shown that this is the point on the curve, 0, negative 3, that both the y coordinate and the gradient are negative 3. Okay, now number 13. Consider this function 2x squared minus x plus 1. Write down the derivative. So the derivative of this function is equal to 4x minus 1. show that at x equals 2, the function is equal to its own derivative. Find the coordinates of the second point on the curve for which the function is equal to its own derivative. Okay, so we just need to program in the calculator the original function and the derivative function. I'm going to do that right now. Okay, now I've programmed the functions, the original function and the gradient function in the calculator. And then I'm going to look at the table. And it asks me, when does the function equal to its gradient, its own gradient? And I see one right here, right? When the function is equal to 7, the gradient is also equal to 7. So that happens at x equals 2. So at x equals 2, they're both functions, the function and its gradient are equal to 7. Okay, so what do you know? That's exactly what it says. It says show that at x equals 2, they're both the same. Okay, now if I want to show that with algebra, what I would do is say y equals, and I would substitute in 2 for the original function. I would say y equals 2 squared minus 2 plus 1, and then that would equal to 7. And then the gradient function, same thing. I would say 4 times 2 minus 1 equals 7. Okay, find the coordinates of the second point on the curve for which the gradient function is equal to the original function. Now we can just scroll up and down until we see the functions become the same value or like close in value. And we can see here that it's not happening over here. Not happening here. It's getting closer. Getting closer. Okay, then they cross. And let's see, did they cross again? No, they don't. So now maybe what we'll do is we will increase the step size. So instead of this, let's do this when we go to 0. So we'll go to 0, and then we'll say plus, and then we'll say 0.5. And now we'll see if there is another point where, there's x equals 7, which we already knew about. Oh, there's one, look. There. They're both equal to 1 when x equals 0.5. So the second point would be 0.5, comma, 1. Okay? All right, number 15. So we have the original function, 2x squared minus x minus 1. And then we're going to find the derivative, y equals 4x minus 1. And then we're going to find the coordinates where the original function is equal to the derivative function. And so again, we're going to program that in the calculator. Okay, so now I've programmed in these two functions, and then I'm going to use the table to see when these two are equal to each other. And actually, there's 2 points where the gradient and the original function are the same. Do you see how it's the same here at 2.5? It's 9, right? And also at 0, it's negative 1. So I'm going to put both of those. So one of the coordinates is 2.5 and 9. The other coordinate is 0, negative 1. Okay, now for 17. Consider the function x squared plus 4x plus 5. So we're going to take the derivative of this function to see what the gradient function is, and it's 2x plus 4. Then it says find the coordinates of the point on the curve, the original function, for which the original function is equal to the gradient. So then we program those two functions, the original function and the gradient function, into the calculator, and then we check to see when in the table the two are equal to each other. And there is a value, okay? And they say of the point, so this is the only point here, x equals negative 1. So when x equals negative 1, y equals 2, and the gradient equals 2. Okay, so that's it for this unit.